let's answer this question. So it says a mixture containing was fed to a distilling column. So this the compositions correspond to the feed, no? Mole C6H6, 15.53% mole C7H8, and 53.93% mole C8H10. At a rate of 100 kilograms per hour. So this is a continuous process, no? We're given... okay, so speaking of basis, we have 1 hour of operation. That is our basis. We have our distillate. Yeah, overhead product, no? This is 68% weight, C6H6. 30.95% weight, C7H8. 1.05% weight. Going back. 1.05% weight, C8H10. Sorry. Yeah, C8H10. As distillation proceeds, a side stream was analyzed to contain side stream 54.59% weight, C6H6. 35.16% weight, C7H8. Okay, that's it. And then we're now given information on the bottom product. Let's write it here first. Contain 1.14% weight, C6H6. I think it's consistent, no? We already have information on how many components we have per strip. Sorry. We have 3. Next, 3.91% weight, C7H8. And 94.94% weight, C8H10. So that is the info for the bottoms stream. Okay, so This is just for the aesthetics. That is what you see in a distillation column. And we are given molar masses. So as you might have noticed, here, everything is expressed in terms of percent mole. The rest, the product streams, are expressed in percent weight. By the way, let's see if this equates to 100%. It is especially suspicious because we only have two components. Supposedly, for consistency, we have three components. So these amount to 89.75 minus 100. 10.25% belongs to the component that is not mentioned here. That is CH10. Okay? So, right now, before we start writing our OMB, our balances, let's convert these into into percent weight. Let's write it here. 0.30 convert percent mole to percent weight in the feed. So 0.3054 mole weight. Recall the formula. Mole is equal to mass over molar mass. We want to express these in terms of percent weight. So mass is equal to mole times molar mass. Our mole is this. We convert the percentages to their fraction forms. In other words, these divided by 100. So we have this in the case of C6H6 in the feed. So we multiply that to the molar mass. What is the molar mass of C6H6? That's 78.11. Calculate. 23.85 grams C6H6. And then next, 0.1515. Let's not write the units anymore. It's already understood that mole will cancel, grams will be left. So 0.1515 times 92.14 is 13.96 grams of C7H8. Next, 0.5393 times molar mass corresponding is 106.16. Calculate. 57.25 grams of C8H10. So what's next? We know we were able to calculate these values. How do we convert them into mass fractions? First, let's identify their total sum. You cannot just assume that they all equate to 100, no? So if you add all of these, they equate to 100, but it doesn't mean that their corresponding mass versions are also amounting to 100. So let's see. 23.85 plus 13.96 plus 57.25. Their sum is 95.06. So as you can see, it's not 100%. Let's convert them into mass fraction. So 23.85 divided by 95.06. And then if you want to make it as percent mole, multiplied by 100. But just this itself is already the mole fraction. Sorry, mass fraction rather. 23.85 over 95.06 times 100 is 25. Actually, let's not. Yeah, let's still express it in terms of weight percent for consistency. 0.9%. Okay. Next, 13.96 divided by 95.06 times 100. The other one, 57.25. Okay, calculate. 14.69%. Next. 57.25. This is 60.23%. Okay. 25.09. Doesn't hurt if we move the PFD a little to the right. But what if I didn't have the ability to move the diagram? It's already drawn, no? How do I make them fit? Let's just make it fit here. Forget about the aesthetic. We need the space. Mole. Sorry. 60.22523 rather. Okay. So now that we have those values, let's write down our overall material balance. F is equal to D plus S plus B. Before proceeding, let's write down what is required. So PFD, we've already finished drawing it, the process flow diagram. Molar flow rates, as in mole per hour, for all the streams. Okay, and then third, we have to calculate for the percent recovery of C6H6 in the product streams, namely D, S, and including B. I mean, technically B is a product, but in the context of distillation, the bottoms stream is basically like the raffinate in an extraction process. It's like the waste, but it's still a product stream anyways. So yeah, F is 100. We need two more equations so that we can input in the calculator so that we can find D, S, and B. So simultaneous linear equations in just not two, three variables. Now that everything is, sorry, this is supposed to be weight. It's easy to find your errors, especially when the next step is trying to identify something from the information that you just got. So everything has to be expressed in percent weight for consistency so that you can form the equation. So overall balance, let's start with C6H6. 0.2509 times F is equal to 0.68D plus, in the side stream, it's 0.5459. In the bottoms stream, it's 1.14. Okay. How about for C7H8? 0.1515 times 100 is equal to 0.309. This is 3093.95. D plus 0.3516S plus 3.91 over 100 B. Okay, so we have three equations already. Let's calculate. We'll solve that other question later. Let's do this first. Okay, ready your calculator? Three unknown equations. 1, 1, 1, 100. Sorry. 0.68, 0.5459, 1.14 over 100. 0.2509 times 100. Okay. Last, 0.3095, 0.3516, 3.91 over 100, and then 0.1515 times 100. Okay. So D is 22.93. 22.93. Everything that we used is in terms of percent weight. So kilograms per hour. S is 16.13 kilograms per hour. B is 60.94 kilograms per hour. These aren't the final answers yet, no? Another way that we could solve this is by converting all of the product streams in terms of percent mole. But right now, we're not in the wrong position either. This is just another way to solve it. We want to express our answers in mole per hour. No? How do we do that? So let's go first with D. Write down it here, and then Okay, I have an idea. So, this is in kilograms per hour, right? And we are given their percentages. All of this amounts to 100%. So technically, if you want to convert this into mass fraction, that is 0.2509, multiply it by D, the total. Let's see, 0.2509 times 22.93 is 5.75 kilograms per hour. Okay, and then after that, we want to convert this into moles, no? I think we are gonna make use of our molar mass. Let's just copy paste. Sorry. Bruh. Copy paste. Okay, so C6H6 molar mass is 78.11. How do you integrate that? 78.11 kilograms per kilomole. So what do you get? 5.75 over 78.11. Kilomoles per hour. So let's do the same thing for these two, and we find their sums. That should give us D expressed in terms of mole per hour. Sounds like a plan, no? Let's do it. 2509. Bring this back. It's our reference. 0.1469, this one. And then times D. $3.37. No need to write the unit anymore. We already know what the units will be. This is enough. 92.14. So this is a very critical step. 92.14 and then over 1. So essentially what we're doing here is, since this is mole, this is mass, divided by molar mass. You see? Mass divided by molar mass, and this is our mole. If you notice, this formula is being demonstrated in our scenario right now. Okay, the next is 0.66023 times 22.93 equal to 13.81. Let's write this in gray because that did not originally come from here. That's my logic. 1 over, so this is C8H10, corresponding molar mass is 106.16. Okay, 0.1301 kilomoles per hour. Okay, time to find their sums. So they all amount to 0.24027. Something doesn't look right. Yeah, something wasn't right. This is supposed to be the feed. My bad. But I think the approach is still the same. Let me just verify what has to be changed in the solution. Yep, a lot actually. This is supposed to be 100. Recalculate. Next, 0.1469 times 100. 14.69 divided by 92.14. 0.1594. Zero point 6023 times 100 is 60.23 divided by 106.16. 0.5674. 0.3212 plus 0.1594 plus 0.5674. 1.048 kilomoles per hour. It says in the instructions, the answer has to be in moles per hour, not kilomoles. So we're not changing anything in the time. 1 kilomole is 1000 moles. 1048 moles per hour. So that is for this. By the way, supposedly everything here in the PFD could be written with a dot. Since this is a continuous process, there is our basis is time of operation, more specifically R of operation. Everything has to be with a dot on the top. But since everything is with a dot on the top, you don't really have to write it anymore. So in the final answer, you can place a dot. Okay, so we were able to find the molar flow rate for the feed. I think you can also say this as that molar flow rate of F. Let's move on to a different stream. How much time am I spending? Let's be fast now. We can't spend much time on a single question like this. So given that D is 22.93, C6H6. Okay, so everything here is in percent weight. So 0.68 times D, 15.59. This is still in kilograms per hour. Multiply it by, divide by the molar mass. K-mole per hour is what we get. Okay. C7H8 is, okay, just follow the same pattern. Molar mass for C7H8 is 92.14. Okay. Then let's find the sum. My back hurts. Convert this into moles per hour. To 78.87. S is 16.13. mass is 92.14. The sum is 0.1898. Convert to mole per hour. Okay. Here, mass fraction is 1.14 over 100 times B. And then divide by the molar mass, 78.11. convert to mole per hour. What is this? Bottoms. Okay, we were able to find the values for letter B, the molar flow rates. Now, percent recovery. Okay. So, of what? C6H6, no? Yeah, specifically C6H6. So in the distillate, it is 0.1996. In the feed, it's 0.3212. Then times 100%. So basically, the formula for the percent recovery is C6H6 in that product stream divided by C6H6 in the feed. Always in the feed. Then times 100. Let's see if my thinking is correct. 1996. Yeah, precisely. The answer is 64%. But I think it's just, at this point, it's just discrepancy. But the approach is correct. Okay, S. Where is S? So C6H6, 0.1127. Same thing in the feed, in the denominator. Calculate. For B, where is that? This one. So let's just copy that entire thing. Okay, then times 100. Okay. So that's it for this one question. Let's proceed to the next. It's currently 8:27. How many minutes have we spent for that question? Wow. I need a break. I'll answer this in the next video.